Homework 9, compound interest, video 6. In the previous video, we talked about how large value purchases or purchases of large items that are really expensive sometimes isn't made by just putting down money and walking away, or putting down money and letting it grow and coming back later and say, hey, look at this extra money I have. Most of the time you make monthly payments. And in a lot of situations, this is called an annuity. An annuity is an investment that grows in two ways. Number one, interest is calculated periodically, meaning at regular intervals. Usually monthly, but it can be daily or weekly or bi-monthly or bi-weekly or a lot of other options. And number two, payments are made periodically. So not only is there interest growing, every time interest grows, you throw some more money on it. Like, I'm going to add some interest. Fine, I'm going to add another 100. I'm going to add more interest. I'm going to add another 100. There's a comment, though, that the frequency of interest calculations and the periodic payments is the same. So in other words, if you're making monthly payments, then you're receiving interest monthly. If you're making semi-annual payments, then you receive interest semi-annually. Basically, you get interest as frequently as you decide to make payments. Of course, this is all set up at the beginning. You can't just arbitrarily make more payments and get more interest. You have to come to an agreement with whoever is going to pay you this extra money. So let's take a look at an example. The previous family, about the $5,000 in the college. The previous family is discouraged about the prospect of investing $5,000 for 18 years, compounded at 2.9% daily. So instead, they purchase an annuity with $250 monthly payments at 3.1% interest. What is the future value? Well, the formula for an annuity, the future value of an annuity, is different than the formula for compound interest future value, because in compound interest, you don't keep adding more money on, you just let it grow on its own. Whereas in an annuity, it is growing while you are piling money onto it. So what is the formula for the future value of an annuity? Well, first we need to define what numbers are going to be used to calculate this. And there are 5. I stand corrected, there are 4. Variable number 1 is a capital R. Not to be confused with a lowercase r. Capital R is the variable for periodic payment. In other words, how much you're paying on a regular basis. In this case, it's $250. Why they use the letter R for periodic payment, maybe for recurring payment, I'm not sure. I wasn't there when that decision was made. There is a lowercase r, so you have to be really careful because both R's are in play. That still stands for your annual interest rate. And as usual, it will have to be converted to a decimal to go into the formula. The T is still the number of years, but we can also call it the term. The term of the annuity. We agree to keep giving you this money for a certain amount of time. In this case, that amount of time is 18 years. And what am I missing? Oh, N. N is the number of payments per year. Number of payments per year. It's kind of like the N in the compound interest formula. How frequently is interest compounded? But since interest calculations and periodic payments have the same frequency, it's going to be the same value. So what's the formula for the future value? In a word or two, a lot more convoluted than the compound interest formula. I realize that was more than 2 words. This is a gigantic fraction. So let's start with the denominator. The denominator is a little fraction, r over n. I'm going to put that in parentheses for calculator reasons. The numerator starts with the capital R. Times, not 1, but 2 open parentheses. And then 1 plus r over n, close parentheses. And you'll notice that looks like the parentheses that was in the compound interest formula. It's not a coincidence, but I'll spare you the algebra to show you why it's there. Speaking of looking like the compound interest formula, this parentheses on the top has the same exponent as before, n times t. But then after all that is a minus 1. Then close parentheses. This last close parentheses closes the first open parentheses. So you can tell it's a little more convoluted of a formula because you've got an addition and a subtraction problem, a double set of nested parentheses, and a fraction on the bottom. However, you type this into your calculator exactly like you see it. So let's substitute the values that we know for this problem and calculate what this annuity is going to be worth in 18 years. Okay. So our periodic payment, in this case monthly payment, is $250 per month. So we'll start with $250 on the top and then do a double open parentheses. 1 plus the interest rate, 3.1%, so to convert it to a decimal, move the decimal 2 places to the left, 0.031, divided by the number of payments per year. Well, if we're making monthly payments, then that's 12 payments per year. Close that parentheses, and then the exponent, open up a set of parentheses, n, which is 12 times per year, times the number of years, which is 18. Close that parentheses, and then minus 1. Now, for those of you with sophisticated calculators that can literally type exponents up in the air, here's where you'll have to be very careful. This minus 1 is not in the exponent. For those of you that don't have exponents raised in the air, this isn't a problem. The closed parentheses will end the exponent. But if you have, say, a TI calculator that types elevated exponents, do not put the minus 1 up there. It will be in the wrong place. It will give you the wrong answer every time. But I digress. Close parentheses, all over the same fraction that we had up here, 0.031 divided by 12. So how would you put this mess in the calculator? Just like you see it. 250 times double open parentheses, 1 plus this division problem, 0.031 divided by 12, close this parentheses, press your exponent button, open parentheses, 12 times 18, close parentheses, and if you have an elevated parentheses, make sure your cursor is out of it, minus 1, close parentheses. This gigantic fraction bar is just a division sign, open parentheses, 0.031, one more division sign, 12, close parentheses, press equals. It would benefit you to actually write down the buttons that you're going to press in your calculator to minimize the chance of pressing them incorrectly. It doesn't completely eliminate the chance of pressing them incorrectly, but it helps when you can see it, read it, and press it. Okay, so 250 times double open parentheses, 1 plus 0.031 divided by 12, close parentheses, exponent, open parentheses, 12 times 18, close parentheses, minus 1, close parentheses, divided by, open parentheses, 0.031 divided by 12, close parentheses, equals. Great googly moo, that's a big number. That can't be right. I'm going to try it again. Make sure I know, okay, I see the number I got, but I'm going to do it again. I think I might have made a mistake. 250 times double open parentheses, 1 plus 0.031 divided by 12, close parentheses, exponent, open parentheses, 12 times 18, close parentheses, minus 1, close parentheses, divided by, open parentheses, 0.031 divided by 12, close parentheses, equals, I get the same answer again. Now, I don't know if you put this in your calculator yet or not. If you haven't, I would recommend pausing the video and doing it. But I put it in my calculator twice. Remember in the previous example when we went from 5,000 to about 8,400? In this case, the future value of the annuity after 18 years, paying $250 a month for 18 years, $72,185.61. And although that won't get you 4 years at some really expensive schools, that is a good chunk of money that you can go to school on. All for paying $250 a year for 18 years. Let me tell you one secret to having a lot of money when you retire. Save now. You probably should have started saving earlier, depending upon how old you are. But the trick to turning small amounts of money into large amounts of money is time. The reason is, and without getting too algebraic, if you were to sketch the graph of a function that has a variable in the exponent, the graph usually goes something like this. It starts growing pretty slowly, but after a certain amount of time, it starts to speed up, and then it starts to skyrocket at the end. You've probably heard a lot recently about how the COVID-19 virus would spread exponentially. This is an example of that. Starts out slow without taking measures to keep it in check and skyrocket. If you want to talk about flattening the curve, I invite you to take my statistics class over Maymester. Selfless self-promotion there. But anyway, when you invest money, this is how it grows. Slow at the beginning, fast at the end. So you want to leave it in long enough for it to start speeding up at the end. Because if you shorten the amount of time, you're not shortening it at the beginning, you're shortening it at the end. So you tell me, what would you rather do? Take off 10 years and have it go that much? Or leave it in there another 10 years and have it maybe double? So that's the secret to having a lot of money when you retire. Invest early and invest often. All right, so we're going to look at one more annuity problem, and that'll wrap up this, this series of videos with the reverse question. If I need a certain amount in the future, how much do I need to start paying monthly now, or whatever the period is?